Okay, so now we're going to look at a very important theorem in statistics known as the central limit theorem, and a new term that we're going to discuss, sampling distributions. So a sampling distribution is the probability distribution of the sample statistic, not the individual values. So whenever we form samples of size n, and we repeatedly do that from a population, we get the sampling distribution of sample means. So we start off with a population with a mean mu and a standard deviation sigma. We take several samples. In this case, we're looking at 5 different samples. Sample 1 and find its mean. Sample 2, find its mean. Sample 3, find its mean. Sample 4, find its mean. Sample 5, find the mean of sample 5. And the sampling distribution, the values in the sampling distribution of sample means are these particular sample means. The properties of sampling distributions and sample means is, first, the mean of the sample means is equal to the population mean. Mu of x bar means the mean of the sample means is equal to the true population mean. And the standard deviation of the sample means, sigma of x bar, is less than the population standard deviation. We expect to see less variation among sample means than we do among individual values. And so sigma of x bar is equal to the population standard deviation divided by the square root of the sample size. This is such an important concept that the standard deviation of the sample means, it has its own special name. It's called the standard error of the mean. Also, the last part of the central limit theorem incorporates the 2 slides before, and also in this concept, if sample sizes are large enough, and in statistics large enough is usually greater than or equal to 30, is drawn from any population. Notice, this is certainly not a bell-shaped curve, and it has a mean mu and a standard deviation sigma, but the sample size is at least 30, then the sampling distribution of the sample means from this population is normally distributed, or at least approximately normally distributed. But if the original population was normally distributed, then the sampling distribution of sample means for any size sample is again normally distributed. Those 3 parts together all make up what's known as the central limit theorem. In either case, right, the central limit theorem says the mu of x bar, the mean of the sample means, is equal to the population mean, and the variance of the sample means is equal to the population variance divided by n, or the standard error of the mean is equal to the population standard deviation divided by the square root of n. So let's look at this again. So suppose we have any population, no matter how funky the distribution looks, but the sample size is greater than or equal to 30, then the distribution of the sample means will be normally distributed. But if the original population was normally distributed, then the distribution of sample means for any size samples is normally distributed, and that means we can use our standard normal table and all the techniques we've learned so far this chapter to find probabilities. So let's use that. Let's suppose we have cell phone bills for residents and they have an average of 63 and a standard deviation of 11. We randomly take a sample of 100 cell phone bills. Let's find the mean and the standard error of the mean. Well, recall, we are not told that this distribution is normally distributed. In fact, it does not look normally distributed. But the mean of the sample means is equal to the population mean, so that should be equal to 63. And the standard error of the mean is the standard deviation of the population divided by the square root of the sample size. 11 was the population standard deviation divided by the square root of 100, or 1.1 is the standard error of the mean. Notice we have much less variability, but it is normally distributed. We have very little variability in the sampling distribution of sample means when the sample size is 100. One more example. Let's find the mean and the standard error for this problem. Now notice it tells us here that training heart rates is normally distributed. So we can use a very small sample, in fact a sample of size 4, to find the mean of the sampling distribution. It is equal to the population mean, which is 135, and the standard error of the mean is the population standard deviation divided by the square root of the sample size, which is 9. Since the population was normally distributed, the sampling distribution sample means is also normally distributed, and it has a smaller standard deviation, so when we draw the bell, it will be a narrower bell. To transform the mean to a z-score, remember we're using value minus mean divided by standard error or standard deviation, and for x bar, the value is the mean itself, x bar. Mu of x bar, remember, was just the population mean, and the standard error of the mean is equal to the population standard deviation divided by the square root of n. I often find it easier to find this piece off to the side and then plug this in instead of using this complex fraction. Suppose we randomly select 50 drivers, and we want to find what's the probability that the average of these 50 drivers drive between 24.7 and 25.5. Let's assume the population standard deviation is 1.5. So now remember the mean of the sample means is equal to the population mean, which is 25. And the standard error is the standard deviation divided by the square root of n, which is 1.5 divided by the square root of 50, or 0.21213. Then we need to find change these, but to standardize these values. So our value is 25.5 minus 25 divided by that 1.5 over the square root of 50, and we get 2.36. Do the same thing for the 24.7. And remember this value here, we already found it a minute ago, it was 0.21213. So we could plug in 0.21213 here and make our calculations in the calculator just a little simpler. We get these two z-scores. Let's look them up in the standard normal table, and we get 0.9909, and we want to subtract out the 0.0793. So the probability that the average of 50 drivers is in the car between this should be 24.7 and this should be 25.5, is equivalent to 0.9116. What's the difference between what we're doing now and what we did at the beginning in 5.2? Well, in 5.2, we're looking for the probability that A1 randomly selected undergraduate had a credit card balance less than 2,700. In that case, we are looking for the value of an X being less than 2,700. We standardize that score, 2,700 minus the mean divided by the standard deviation. We get negative 0.42, which gives us 0.3409, and so that is equivalent to, so the probability that an individual person has a balance less than 2,700 is about, I don't know where this 0.3372 comes from. I'm sorry, these are slides provided by the publisher and I can't change them. But what goes down here is the value we found in the table for 0.42, and I believe it's the 0.3372. And so about 33.72% of individuals have a balance less than 2,700. But suppose now we select 25 undergraduates to see what the probability that the average of those 25 graduates have a credit card balance less than 2,700. So the first thing we do is we find, let me go back. First thing we do is find, remember the mean of the sample means is 3173, but the standard error of the mean is 224. So now let's standardize the 2,700. Remember in here is the 224, so we can do that minus that, divided by the 224, and we get negative 2.11. Look up negative 2.11 in our standard normal table, and we get a value of 0.0174. So just a little over 1% of samples of size 25 would have a balance less than 2,700. Right? So a 34% chance that one person does, but a 2% chance that an average of 25 balances would be less than 2,700. Now notice less than 2% is less than 2 standard deviations from the mean, so this would be an unusual event. All right, that's the end of section 5.4. Now go to Course Compass website to My Math Lab and do the homework set for 5.4. This is the end of our lectures for Chapter 5.